Hi, welcome back, YouTubers, OpenFOAMers, to this video of discussion of algorithms on pimpleFoam. So we were trying to build some basic concepts back in the last few videos. Firstly, on what an inner loop is, what an outer loop is, what equations we are actually solving in the Navier-Stokes, and what is a simple algorithm. Simple algorithm basically goes through this whole loop, the outer loop, as many times as you need to until convergence. So per time step, okay, if you are doing a transient simulation, per time step, you're going through this whole thing. If you need 50 times to solve the thing to convergence, you'll go through the outer loop 50 times. All right, and that's solving the momentum equation 50 times. So that's what a simple algorithm does. This is a very stable algorithm. It can regardless of the time step number, you get a solution. That's why you can use it for steady state. So yeah, there may have been some confusion in the way I was explaining it, but okay, let's go for steady state. Let's compare steady state and transient. So pimpleFoam was originally designed for steady state, so it can solve the velocity field over and over again because it goes through momentum equation many times, and it solves the Piezo and continuity equation to feed back the pressure to solve the momentum equation over and over again. So regardless, it can solve the what do you call that, steady state, regardless of where your initial gas is. Okay, so that's a simple algorithm. It goes through the outer loop many times. Now, of course, you can apply the same strategy to transient simulations. So per time step, you will keep solving the outer loop until you get convergence. All right. So, okay, yeah. So per time step, you solve the outer loop again and again until you get convergence. However, this methodology is pretty slow, and due to the nature of transient simulations, if your time step is very small, you don't really need to solve the momentum equation so many times to get convergence. All right, so that one is more of a trick in numerical methods, that when your time step is very small, you don't need to solve the momentum equation so many times in order to get a stable converging solution. So what actually takes advantage of this is the Piezo algorithm, where based on a small Coulomb number, which is coming from a small time step, you solve the momentum equation less times per time step in order to speed the calculation up if your time steps are very small. So if you want a small time step, the way to go is Piezo. And Piezo algorithm gives you speed. It'll give you speed either way. It'll give you speed, but the only way it is stable is if you have a small Coulomb number. So let's stable. So stable if you want a small Coulomb number. Okay, so if you reduce your time step enough, it will be pretty stable, and you don't need to solve the momentum equation again and again. What is the advantage of this Piezo, and why would you want a small time step anyhow? If you want to see, let's say, a turbulent phenomena, or if you want to see phenomenon like what do you call it, vortices, with a very small characteristic time. Let's say it takes 1 microsecond for a vortex to kind of turn about itself, and if your time step is 1 second, you will not see the vortex actually forming. So if you want to see the vortex forming, you need to reduce the time step to maybe about whatever the characteristic time is. Could be 1 millisecond or whatever. Then you can see the vortex forming. Okay, but if you're going to use that simple algorithm to go for this small time step, that means you'll be solving the momentum equation many times. Then the computation cost is going to be expensive, So and that's kind of overkill, right? That's overkill. So to make use of this small corona number, and because of the small time step, the velocity fields will not change so much as compared to the previous time step. You can keep solving. You just solve the momentum equation once and the Poisson equation many times, so that you speed things up. That works well if the corona number is small. If the corona number is not small and you apply this trick, then likely you will have a diverging solution, meaning the velocity fields will blow up and you will not get a solution that makes sense. Alright, so this Piezo algorithm does help you to speed up. If your time step is required to be small. But what if you want a sort of a in between kind of a solution? You want a bigger time step, but stable solution. So you want a stable solution, yeah, sure, you can use a simple algorithm. But you want a blend between stability and speed. Okay, you want a stable solution, which a simple can offer, but you want the speed advantage of Piezo, right? You want the speed advantage of Piezo, but the stability advantage of the simple algorithm. So the solution is what the OpenFOAM people have come up with is something called the Pimple algorithm. So you want a larger time step, yes, but you want the stability of the simple algorithm, the speed advantage of the Piezo algorithm. So what the OpenFOAM people have is the Pimple algorithm, which you see here. Okay, the Pimple algorithm is the hybrid between simple and Piezo algorithms. So what does the Pimple algorithm do? Okay, so remember the Piezo algorithm, you cycle through the momentum equation once, and then you cycle through the Poisson and continuity equation many times. So for a small corona number, that's perfectly fine. But once the corona number exceeds 1, and you don't want all the small time steps, then okay, you kind of got a problem there. The corona number is more than 1, but I don't need a small time step, but I want the solution to be stable. So this is good for corona number. Okay, let me give myself space. Maybe I can paint it black next time. Okay, so this, yeah. Oh no, okay. Yes, this is much better color scheme. Let's say you have a corona number bigger than 1. Okay. Apologies. Let me go and color everything in properly so it's not such a distraction. Alright, I've changed the color scheme. Hopefully it looks nicer. But anyway, we have the case where we want our corona number more than 1, but we still want the stability that's offered by simple foam. Yet we also want the speed advantage of Piezo foam, where we don't solve the momentum equation so many times. So Pimple is a hybrid between simple and Piezo. So maybe Pimple goes something like this. Alright. Every time you cycle this algorithm, okay, let's say you have 1 time step here. This is a transient simulation, 1 time step. Okay. Then you have an outer loop. Okay, 1 times outer loop. And basically, let's say you have 5 times of the inner loop. This is the Poisson plus continuity. And this is the momentum. Now, if we were to run it like that, this is we only run through the momentum loop once, and this is a Piezo kind of a loop, because we only run through the momentum equation once, and we run through the continuity and Poisson equation, the pressure equation, 5 times. So whether it's 5 or 50, as long as we run through the momentum loop once, that is a PISO algorithm. Now, if you want the stability of the simple foam, you can do a hybrid. Let's say you take this whole algorithm, and now we cycle it. We repeat it 5 times. 5 times repeat per time step, right? Five times repeat. It can be 5 times, 50 times, whatever, as long as this the loop, this whole thing is repeated. Okay, so that actually combines the speed of, you have the characteristic of running the inner loop more times than you run the outer loop, which is the momentum. So so that is this whole red box is the Piezo kind of thing. What makes it Pimple, where we have the simple merging with the Piezo, the methodology of simple foam, is that we run the momentum equation more than once. So if we run the momentum equation more than once, we can guarantee ourselves that, okay, this loop is going to be pretty stable, even with large Courant numbers. So this is good for, it will be stable regardless of Courant numbers, provided we repeat the momentum equation sufficient times. So this is what the Pimple algorithm is basically all about. It helps us to deal with large Courant numbers. And so if we can have larger time steps, and we don't want to run this Piezo iteration so many times, we want larger time steps, we want stability, and we want a blend of that and speed, pimpleFoam is the way to go. So that is basically what the Pimple algorithm, the simple algorithm, and the Piezo algorithm are about. All can be used for transient simulation, but pimpleFoam gives you the most flexibility. Of course, if you repeat the Pimple loop once, it is basically a Piezo loop. If you repeat it more than once, it becomes a Pimple algorithm loop. So there are certain advantages and disadvantages depending on how you tweak this loop. And for that, I'd like to bring you to this document here. This document here on how to use this Pimple algorithm correctly. So I'm going to copy and paste this link again here. Yeah, this is a very important reference, which I kind of mentioned in the first video. Okay, so based on the knowledge that you kind of gathered, the introduction knowledge on the simple foam, Piezo foam, and now the Pimple foam, we can see we can kind of read this with some kind of background knowledge, and we won't get so confused. So basically, they have a new case, all right, and we need to tell OpenFOAM, right? Remember, I told you in this Pimple algorithm, you need to tell OpenFOAM you need to tell the solver, rather, not just OpenFOAM, any kind of solver, how many times you want to repeat this loop, and how many times you want to repeat the inner loop. Okay, so remember what the inner loop is. This step 2, 3, and 4. This is, remember, step 2, 3, and 4 is the inner loop, where we just solve the Poisson and the continuity equation. And the outer loop involves solving the momentum equation. Yeah, outer loop involves solving the momentum equation. So you need to tell OpenFOAM, okay, how many times do you want to solve the outer loop, and how many times you want to solve the inner loop. So as with always, you take a look at the what do you call that? Let me clear the left hand side first. When we have this FV solution file, we have a correct 5, correct phi here, entry. We have not talked about this at all. But we have this n outer correctors and n correctors. So what are these n outer correctors? This was the outer loop I was talking about. Meaning per time step, how many times do you want to solve this momentum equation? Alright, this is to help with the stability thing. N correctors is how many times you want to, like per iteration, in that red box I was talking about, in this red box here, how many times do you want to solve the inner loop, which is the Poisson and continuity equation. So this will help with the speed somewhat. Maybe you don't want to have it 5 times. The normal recommended is like 1 to 3. 1 to 3 times solving of the inner loop. So let's go through this. So this is, we basically have the case of trying to convert a Piezo foam case into a Pimple foam case. So if we were to delete, okay, we go to the, okay, if you go to your tutorial file, we go to the Pitts Daily case, which is what they are doing, and we go to system. Oh, we can use the VI straight. System and FV solution. Right. So we have the Pimple entry here, which is one additional entry you need to add in addition to whatever you have normally in your Piezo foam directory. Okay. VI system, FV solution. Yeah. So in your Piezo foam directory, we also need to specify, okay, how many times you want to go through the Poisson and the continuity equation. In this case, it is 2. Okay. So this is based on the n correctors entry that we see here. Okay. So if we were to delete this entry, right, the number of characters will default to 1. So if we were to give this, if we were to delete this and we just leave the Pimple entry as such, yeah, if we were to delete this entry as such, then outer characters will be set to 1, meaning to say at least it will run through the momentum equation at least once. And characters will be set to 1, meaning it will run through the Poisson and the continuity equation at least once. Alright, but this is basically a Piezo mode kind of an operation. So yeah, if we, and this basically say, if we have a case that the Couron's number, the maximum Couron number is set to 3, the equation, the simulation will blow up. Okay, the simulation will blow up. So we need to set it to less than 1 because this is the Piezo mode. Remember, Piezo mode only runs through the momentum equation 1 time. Alright? So let's say the document kind of goes through the second case, case B, where you set the n characters to 2. And that's usually the featuring thing, the main feature of Piezo. Piezo foam actually increases the speed of convergence. So if your solution were to converge, it will take less iterations to get to the convergence for that particular time step. So yeah, oopsie, which means you have to repeat this box, this red box that. So anyway, actually no, yeah, we run the momentum equation once and we run the Poisson and the continuity equation twice per time step. Okay, so if we do this, it may become more stable. Yeah, it may converge, the solution may converge better because we run through the Poisson equation again. That means we are iterating in the Poisson equation without going back to the momentum equation. The results may definitely be better than as compared to iterating through the Poisson equation once, but it may or may not give us a stable solution. in this case, as we go along the time steps, one iteration per time step, it seems to be okay. Now, in case C, it shows you the way you actually want to include the simple algorithm with your Piezo algorithm. In other words, we loop through the momentum equation more than once per time step. So in this case, n outer characters equals to 2, n characters equals to 1. Meaning to say, I'm going to run through, okay, let's say in this red box again, the repeat is 2 times. And this inner box, we go through the inner loop once. So every time you run through this red box, you have one momentum equation solved and then one Poisson plus continuity equation solved. Run through this whole thing twice. And that is what this is telling you here. It runs through the momentum equation, it runs through the Poisson equation, it runs through the correction, runs through momentum again, Poisson again, and it's corrected. Okay, so that is the beginning of running us through the Pimple loop, because we have elements of the simple loop where we run through the momentum equation more than once, and we also have this n characters equals to 1, or we can set it to 2 or 3 if we so wish. Okay. Now, according to this tutorial, it says that setting this up does not necessarily give you the stability that you want, even though you cycle through the momentum equation more than once. What's going on here? So in case C2, we actually need one more ingredient in order to make sure our Pimple algorithm will become stable and converge to a solution. So case C2 will complete the Pimple mode. We need to add relaxation factors for the fields and equations. So again, this part we can more or less understand. The n characters equals 1, n outer characters equals 50. So n outer characters meaning to say we loop through the momentum equation plus whatever, however many times you want to run through the Poisson equation, 50 times, right? However, there's one more ingredient. The other ingredient they have added in is this thing called relaxation factors. And that will actually make the equation more stable. Now I can go through relaxation factors in the next video. So because this video is already 20+ minutes, so I'll see you guys next time. Thanks for watching.